Hello and good afternoon, everyone. Today I'm demonstrating the neural network that I'm simulating to complete our assignment on neural network. But before I tackle that, I will see what is my assignment on neural network or what are the objectives. Let's see. Ah, iterations in neural network. So we have three questions or three objectives to find out. The first is what is the value of activation function after 100 iterations? Number two, in what iteration from 1 to 100 does the neural network has best performance? And number three, how many input does the neural network have? Hmm, Now let's see. Now we're using the neural network simulator that our professor has done. And before foremost, let me introduce myself. I am Einstein Stephen Macho Di Coblete, BSIT, second year. Now, we can see here is the neural network simulator that our professor has graciously provide us or sent us the link for our, to do our assignment. We have here the is the feed-forward neural network that designed to learn the XOR functions, a classical problem in neural network training that requires a hidden layer to solve. First, here, it's been separated by three parts. The first layer is the input layer. The input layer has two neurons, which is represented here with X1 and X2. As you can see, this already answers our question number three on how many input does the neural network has. We know an answer, which is two. The neural network has two inputs. This represents the two values we feed into the zero function. Now, we go to the second layer, which is the hidden layer. The hidden layer composed of three neurons represented by A1, A2, and A3, or A raised to 2 and 1, A raised to 2 over 2, or A raised to 2 over 3. So this is crucial because the XOR is not limited separately. We need these hidden layers to learn the complex XOR patterns. This will help us in the identify on from input 1 to finally get our layer 3, which is our output layer. So we can see that the output layer is we only have one neuron that will give us the XOR result. And as you can see on the side, this table, this is the XOR training data. As you can see, if the input is 1 and 1, the output would it should be 0. And if the output is 0 to 1, and the output would be 1. And if the or input is 1 and 0, the output should be 1. And if the input is 0 and 0, the output should be 0. So it's like thinking of the 0 as false and 1 as true. So moving on. Now, as we start the simulation, as we click from in the written 0 to, let's say, to 100, so that will take a while. Now I'm starting the training by clicking to 100 iterations. What does the neural networks learn through the backpropagation? We can see the error decreasing and the neuron getting better and predicting the correct XOR outputs. See? Notice how the statistic update in real time as it updates. Oh, the current input count. And as you can see now that it's almost 200. There, now it's begun to the iteration is now 100. See? Uh, why is the XOR special and challenging per se? Before we run the training, let me explain why XOR is such an important problem in neural network. Here, the XOR challenge why we need the hidden layers, the XOR exclusive, so exclusive OR per se for the XOR or means one of or the other, but not both. So in simple terms, if zero is one and one is zero means both inputs are on. So exclusive fail. But if the input is zero and one and the out is one, it means only one input is on. And if same with one, if the input is one and zero and the out is one, that means only one input is on. And if it's the input are both zero and the output is zero, it means neither input is on. So why this is hard? You cannot draw a single straight line to separate the form on zeros and exclusive or. This is called not nearly separable. A single layer perspective, just input and output, cannot solve this. We need the hidden layer, which is here, to create a curve for decision boundaries. The hidden layer solving this by the three hidden neurons learn to detect the different patterns. As you can see, on neuron 1 are both inputs high. On neuron 2 is there are specific inputs pattern. It asks those questions. Is for neuron number 3. Are the inputs different? Each neuron represents a different question onto getting a specific answer, especially for our output layer. So our first. So those three are important to get our final answer. The output neuron then combine those three patterns detected to solve the exclusive OR. So it's like comparing a graph literally. We're comparing three different answers to get the final answer. Now, when the training completes, now perfect. The training has complete all the 100 iterations. Now let's answer the assignment questions based on the actual simulation results. So as we can see on question what is the value of the activation function after 100 iterations? Let's see. Oh, let's see. So for our hidden neuron, so A2 over here, it says around from the diagrams around, let's say 0.7 is 66666 or more precisely 0.7777. And then for our hidden neuron on A2 here is around, let's say 0.745 or let's more precisely more about 0.75 or more or less. And then for our hidden layer neuron, which is around, 8 to 3, around, let's say, 0.2. So 0.32. And then the output neuron on over here on our last, compared to the others, is around, let's say, is a final. So the output is 0.27. So there are three different outputs. So 0.75, 0.28, and 0.41. The key activation functions values are visible in the training network weights and neural steps, as you can see. With all of these answers here, the tree from each neuron on the hidden layer give us the results. Now for question two, in what iteration from 1 to 100 does the neural network have the best performance? Based on the training progress, I observed the neural network performance involved through the 100 iterations. The exact best iteration would be shown in the error tracking, but we can't see that, especially on this here, as we don't have. Oh, we have error tracking here on 6. So let's see. Let's go to page 6. Where is it? 5x. Let's see. Errors in hidden layers. So this is the formula for hidden layer. Now let's see. So this is the error, as you can see. So the error is on if one input is 1 and 1 in the output 0. So that's the error that cured. So now, as you can see, oh, okay. Now, for our question number 3, how many input does the neural network have? As you established the answer for this, which is around 2 inputs. This corresponds to the 2 variable needed, which is x1 here and x2. What we have witnessed here is the back propagation algorithm in action. The neuron stated with random weights and through 100 iterations of training. It learns to approximate the exclusive OR functions. Here, look at our final test result. You can see how close the neuron output are to the target value, which is here on the table. So 0, 0, 0, or it's more precise. Input 0 and input 0 because the result is in have target 0. If input 0 and input 1, the target is 1. And if this 1, input the 0, target is 1. And if the target of 0 and a 1, target of 1 is 0. Analyzing the details of backpropagation process shows here the iteration 100 with full mathematical breakdown. Now, I'll walk through the detailed mathematic process shown in the simulation after 100 iterations of training. Forward fast how iteration flows. The term break is count in simple terms. Simple terms. Step 1, we're feeding in x1, 1, and x2, 1. Testing what happens when both exclusive OR inputs are 1. Step 2, hidden layers. Hidden layers 2. So here, this is where the magic happens. Each hidden neuron breaks down input and process them. So think of it like this. Each neuron say, let me combine this input with my learned way. The first neuron up here on A21 is quite active, as you can see. See, it's quite high. On our second neuron is moderately active. It is more on the middle ground, as the middle. On our third neuron, as you can see, is a bit more is less active, as you can see here. the this the sigma is the sigmoid function is just squish squishes any between 0 and 1. And for our step 3, which is the output layer, is the final neuron combination of three hidden neuron outputs. This is like voting system. So each of the three hidden neurons votes which is the active value. So in the final result, as you can see, is very close to the 0. So which is the correct form of which is, as you can see, is the closest is this 0.11. Just the yes, which is closest to the 0. So which is the correct answer for the exclusive OR of 1 and input 1 is 0.11. Now, the back propagation on how the neural network learns from mistake. Now, how come the learning part, this might seem complex, but think of it like this. So for step 4, the cost calculation of, let's see, of this. So E equals to 1,139,2,895. This is like asking how wrong were we? So how wrong? Target has 0, we got 0, 0.1139. So our mistake score is, let's say, 0.975661. Now for our step 5 is the output error. So is here number 5. Number 5. We just calculate here. Oh yeah, here. Output layer. Oh yeah, sorry. The calculation cost is around 0.2023308. And the output layer is for our 6361. And then for our output layer, here's our place. So 0.17, no, 1472415. This calculates how much should we blame the output neuron for this mistake. So the negative signs, you were too high. Next time, activate less. So this is our error and output layer. That is our step 6 to 80 zero propagation. But first for step 6 is, oh wait, go to the step 6. Oh no, let's see. That's for one is 0, all that. So if it's quite different when we go to iteration 100, as you can see, the error in output layer 1 is negative 0.147, but in iteration 100, it's 0.112. That's a 121. And for error in hidden layer is for the first one is negative 0.02. And for the second and third is 0.008, 0.011. If we compare it to the other, it's almost similar and quite different at the same time. They have a huge difference. Okay? Same with our 7 and 8. 8, 7, the error with respect to weight between hidden and output layers is 0.09 and 0.096 and 0.07. What are the negative? For iteration 100, it's negative 0.04 verifying in negative 0.066. That's a big difference from iteration 1 to iteration 100. And for next, now for step 8, what error is equal to weight between input and hidden layer. See? It's quite huge. Now, it's bit more complex, so let's more on simplify it. So, like tracking back responsibility through the network. So, it thinks of all the errors, which is like asking a question earlier. Which hidden neuron contributes to this mistake the most? So it calculates, and what's the output? So it's here that what was the calculation output happened. Now let's go to step 9 and step 100, step 10. So let's go to step 9. Right. Okay. First, we do it iteration 1. Okay. Iteration 1. Oh no. Iteration 1. Oh no, it is iteration 1. Oh yeah. Or, I don't know. Iteration 1. Calculate the error with respect to weight, yeah, right. Update the weight between hidden and input layers. Finally, we have adjust all the connection strength or the weight. Think of it as the next time listen more to neuron than help. So less to neuron that didn't. So let's see the difference in the two. This is so it's first is 0, 1, 1, 1. So zero now it is 0.18. Then it's 0.16. 400 is 0.7, or and then negative 0.734, and then negative 0.45. That's a huge difference from the first step would be huge leap, then huge go down. And then for step 10 is 0.07, 0.25. As you can see, in compared to the 100, it's almost always in the negative. So yeah. Now understanding what the neuron actually learns. So after 100 iterations, let's see what this final way means. So the hidden layer, these numbers tell us the hidden neuron how much attention to pay to each input. So some weights are positive, like you can see here, the weights means if this input is high, get more excited. Then some are negative, like as earlier means if this input is high, get less excited. This creates different personalities for each hidden neuron. For the output way, this tell the final neuron how much to trust each hidden neuron. So why this works for the exclusive or the network has learned to create pictures, detectors, and hidden layers. One neuron might detect both inputs are the same, another might detect inputs are different. The outputs neuron then combine those features to solve the exclusive OR. So let's say simple check for input 1 is to 1. The output is here. Okay. The output is 0.48. So it says correct on exclusive OR of the input of 1 in 1 should be 0. So which is correct. If you simplify this is 0, which is correct. So here now this graph shows us on what we needed and for the neuron network. Let's see. I can provide the answer for our three assignment question on answer one. Which of the activation functions after an iteration form the decal calculation in iteration 100? The output calculate calculation and activation, which is 0.48. Oh no, wait, yeah, 0.48. With all of this comes being compared, final answer is there. And then for a hidden layer, the activation is this 0. Negative 0.78, 0.05, negative 0.73, 0.93, 0.33, and negative 0.5. For our input is 1 is to 1, the neuro network correctly output approximately 0.488, which is close to the target value of 0. For answers to the best performance iteration, the network shown continuous improvement throughout all 100 iterations by iteration 100. The cost function reached about 0.118. Then demonstrate the success learning. The network achieved this because performance in the final iteration with iteration 100 showing exactly exclusive or performance recognition. For answer 3, number input, the neuron network has exactly two inputs, which is x1 and x2, clearly visible in both the neural network simulated diagram and mathematical calculation where we see x1 is 1 and x2 is 1 being processed. So, yeah. And for simple analogy for understanding or to summarize this to simplify is think of neural network like a team making decision. So imagine you trying to decide, should I go outside based on two inputs? Is it sunny or is it raining? And for me, I can give this an example in real life. So I can't go outside because it is raining. So yeah. So the input neuron are like sensors. They just report a fact. So the hidden neurons are like advisors, each with different expertise. Advisor one might think it's sunny and not raining. Go out. Advisor two might think if weather conditions are mixed, stay cautious. Or advisor three might focus on extreme condition. Both or neither means stay in. So on the output neuron, it's like you making the final decision. Should I listen more to advisor one, two, or three? The learning process is at first you don't know which advisor to trust or at random weights. So each time you make mistakes, you adjust. Next time, I'll just I'll trust advisor two more, advisor one less. After 100 decisions, you'll learn the perfect exclusive OR strategy. That's exactly what happened in our simulation. The network learning with advisors through hidden neurons who trust for the exclusive OR decisions. That is all, my friend, and thank you.